What does it?
Where is that? Let's see. Mhm. Working.
When this is here, so it's very good.
Okay. So
He said, we're light. He said, they said, we're white.
so let me see if I can make this a bit bigger. This is okay. So just a reminder that this Thursday. So on Thursday you have so the idea for recitation would be probably for like the first hours or so you have like a workshop problem kind of similar to last time where you can work in groups or individually if you like, and then there will be a quiz in the last 20 minutes of class. I sent like an announcement with the quiz information. So like usually my idea for the quiz problems will be more either based on examples that I did in class or like, but or something similar related to an example I did in class, but they will always be like announced ahead of time. So for like, since this is like the first quiz and we still haven't covered that much, it's just like two questions for you to study, which are the ones I mentioned on the announcement. So one was like how to find the volume of a sphere, which we did in class last time. And the other one is how to find the volume of a cone, which actually is like the one I'll start with today. So, but, usually probably for like and subsequent quizzes, like I'll give you more problems to look at, but it will always be kind of like, I don't know, 5 or 6 or 7, but based on like things that we have done. And so like the quiz will be kind of like one of those problems. It won't be like any different from that. So just keep an eye on that in general. But again, like for the first week or for the first quiz, there's not many to look into. So what I was saying last time, just to remind you quickly about that. So we were looking at the volume of the sphere. And the idea is that if you want to find the volume of the sphere, there are different ways to break up a sphere. The one that I used was that if you take a sphere, like you can make cuts with the plane that gives you like discs, like the ones that you see here. And then you kind of like imagine thickening up look those discs a little bit. Okay. Oops. Where is the coloring? And then the volume, like, if you break like, so you imagine kind of like breaking up the sphere into kind of like, or approximating the sphere by these like thickened discs. And then the idea is like that the volume is in a sense like a sum of the volumes of those discs, but like as an integral because like you do have to like shrink the discs more and more for like the approximation to become better. But the idea was to set up like kind of like the volume as like an integral of like the area of like one of these disks. So I think I made it from negative R to R last time. So the volume was like the integral from negative R to R of A of X dx, where here A of X was kind of like the area of like a disk at a distance X, at position X, let's say, from the origin. So like, if you think of like the x-axis as passing through the sphere, here you have 0, and then this disk is like at like distance x from 0. And there are other ways to set it up, but that's like kind of like a convenient way to do it. And so that can be generalized a bit, and that's called like the cross-section method for finding the volume of like a solid. So let me call this. So the idea is like if you have like a solid, it doesn't have to be like a sphere. I'll kind of draw it more like something like a tube. So just like imagine you have that solid, you want to find its volume, so you want to find like kind of like how much stuff is inside this like on the interior of like this solid, which is like kind of like a tube again in this case. So the idea is kind of like analogous to the case of the sphere, like you imagine like cutting it, okay? So like you take a plane and you cut it. So there's like a cross section, which in this case it still looks like a disc, and that's because in most of the cases we'll work with, the cross sections do look like a disc, but you see like they have like different sizes, like depending on where you make the cut. So like this is like one of like the cross sections of the solid. And so let's say you have like the x-axis here. Maybe this is like where the origin is. And then this is like the solid starts at a position A from the origin. So maybe here's A and here's B. And then this one is like at location X with respect to the x-axis. So let's call A of X the area of like the cross section at distance X from origin. So far, so good. Is like the picture making sense up to this point. So again, it's like you're just making cuts, 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 cuts. And then you kind of like imagine that this kind of like gets thickened out a little bit. So the thickening was kind of like it's kind of like just take the disc and move it by some amount, because this is calculus, like the amount that you move it is called delta dx, because it's supposed to be really, really small. So like the amount that you move this is dx. And so the idea is like, like it's like you would do the same for the others. And so you kind of like are approximating the volume by the volume of these like thickenings of like the cuts that you made. So like I'll do another one here just to kind of show it. And another one here. And so the idea is that to approximate the volume by the volume using the volumes by adding together of these thickened cross sections. But like the volume of one of these like one of these pieces is just like the area times how much you moved it. So it's like area times this plate, like kind of times the distance. I mean, if you turn like your head 90 degrees, it's kind of like area times like the height, you know. Like sometimes it's actually better to kind of like turn everything upside down. So this is like the cross section. And the height is the x, so base times height, right? Like that is the volume. The volume base times height. Like, of course, like in the picture, I just kind of made a quotation. So, but it is like kind of a bit better. It's more standard to look at it that way. So, yeah, sorry. Oh, I mean, in practice, like you mean to approximate the. Oh yeah, you could like. I mean, like it does. Like the integral won't depend on like how whether you use the left-hand side rule or like the right-hand rule or like the midpoint rule, like usually that's one of like the features of like these Riemann sums, like that they are independent of what you would call like the partition. Like yeah, in this picture, I'm kind of like using the left side just because it's kind of like easier, like for psychological reasons, because I usually write from left to right. So like it's kind of like better for me to think about it that way for drawing the pictures. But yeah, you could have like taken like, let me see if I do it without but you could have like done it like yeah, like in a different way where like you use like say the midpoint or something like that. Like, it doesn't look exactly the same way. But yeah, it's kind of harder for me to draw it that way. But it would work fine, yeah. I mean, you do have to be well, like yeah, you kind of have to want to be consistent, although like this is, you know, the idea for it to work is that you kind of broke the interval AB into pieces, right? Like mini intervals, and then you choose like a point from each interval. So it doesn't have to be kind of like the same point in the sense, it doesn't always have to be the same, that left endpoint of each sub-interval. Sometimes it could be the left endpoint, then the right endpoint, then the midpoint, then 1/3 for one of the endpoints. So like the rule, like you just need a point on each interval, like a representative. And like the integral, if it converges, like, or like it exists, like it will be independent of like the partition, which is actually how that's called. Is that answering your question?
Yeah.
Yes.
I mean, can that also be used to, I mean, we were taking like, so you said that, whether you take all of them at the left, all of them at the right, doesn't really matter, so. Can we understand that it's just like really breaking it down into like such infinitesimally small pieces?
Right. Yeah, like the thing is like, like the difference, because right, like in the, of course, like in a finite, when you do finite cuts, it does matter, right? Like they won't give you the same answer whether you do left endpoint or right endpoint. The thing is like the difference between doing the left endpoint or the right endpoint versus like the midpoint, whatever, in the limit goes to 0. So like that's what allows everything to kind of like converge. You're right, because like the partition, like actually, like again, I'm so bad with the right endpoint. I don't know why. But I guess what would this like be like the right endpoint, I guess? Something like that, right? And so you see, like, there's kind of, yes, it's true. There's kind of like this small gap between them, but that will shrink to zero if like the integral is to exist, you know. In fact, if it didn't shrink to zero, you cannot find the volume of this solid in a sense. Like there's no volume. Like there would not be like a good answer to give for the volume. Things with volume are things for which this works. So it's kind of, it may sound like a little bit circular, you know, but that's kind of like the idea. Is that okay? Is that making sense with everyone? So, you know, the good thing about Riemann sums is that you forget about them. So like, you know that they're kind of like in the back of making everything work, but you don't care about it, you know, like you just, because it's like an integral at the end of the day, to do like an integral, you just like finite the derivatives. Well, it's kind of more important. It's kind of like the idea of like, what the point of like the integral is like, the idea behind an integral is to break something into small pieces, which you want to add, but like for it to become a better approximation, the pieces that you are adding have to kind of like shrink in some sense. And that is controlled by shrinking, like thinking of the x as really, really small. But yeah, so like, just like I can draw that same picture on the board. So like what I'm trying to say is like the volume of one of these pieces, which is kind of like a, what, like a solid cylinder. It's like kind of like base times height. And so like in this case, like the base, you think of it as being a of x, and the height in this case, like is dx. And so you're adding all these pieces. Oh, by the way, it's kind of like useful to think about units, like what, you know, with integrals. So like, what are the units of length of area? They are kind of like length squared, right? Let me write that down. Okay. So this has units of length squared. Right? Dx is like a little bit of an interval, so it has units of length, like in the way I'm thinking about it. So this has units of length, right? And so length squared times length gives you length cubed, which makes sense because we're trying to find the volume. So whenever you set, you know, that's something like, which is sometimes unfortunately lost when you're doing like a math class, because like we don't work with units in mathematics, but you know, if there's like a, if you were to put units into things, like that units better come the right way, you know. So if you're actually claiming that you're computing volume, yeah, you should end up with something that has units of volume. So this has like units of length cubed. No, so it's kind of like useful whenever you write like a formula to make sure like, you know, it does come with the right units, you know, which people call like dimensional analysis, among other things. Okay, but what this formula gives you is kind of like the volume of one of these pieces, but you don't want just like the volume of one of these pieces. You know, you want the volume of this piece plus the volume of this piece plus the volume of this piece, blah 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 blah. But again, for it to really work in the end, like you kind of like integrate it. That's how you really want to think about it, because there's secretly a limit being taken in the back of like the calculation. So like the volume in this case would be the integral, let's say from A to B, because like that is like in this picture where I determined the bounds for x. Like, so the solid started at A and ended up at B. So it would be the integral from A to B of A of x dx. So, but again, like you want to think of that as a sort of like sum of like mini volumes or infinitesimal volumes, which is really what you would call them. Is that okay? So far, so good. Questions up to this point? Okay, so again, like I did it last time for the sphere. I'll do it now for the cylinder that I had promised you to do it, just to show you how it works. And the thing with these problems, kind of like I can tell you where the difficulty lies. It is like, how do you find a formula for A of x? because once you have like the formula for a of x, you do the integral, and this is not, they are not like crazy integrals. If they're kind of like volume problems, the words that you may need is like a u sub, but usually that doesn't happen for this type of problems. Like they're just like straightforward integrals after you have a of x. So like finding a of x is kind of like the hard part of the problem, and because you have to get creative and there are a few options. So let me write that down, like just to keep an eye on. So for these problems, the idea is to find a formula for a of x. So usually that will not be given to you. So like that's where like you have to, like that is where like the effort of the problem typically goes to, like finding a of x. Okay, so yeah, let me show you that with the cone. Of radius r and height h. And this is like the other problem that I said you should study for like the quiz. So um and usually for this type of problems, I do like not giving specific values to, like, say, for example, the radius or the height, because that way you can actually see what the formula is. If you just put like radius equals 2 and height equals 3, that kind of like the answer will hide what the formula is. So it's kind of like, better to like give letters to the different like aspects of the solid rather than just like give specific values to kind of like appreciate what the formula is supposed to be. So let me draw the cone first. So I'm thinking of a cone like where the base, like the base of the cone has like, it's a disk of radius r. So that's what like the r here represents. And then the height of the cone is h. Okay, so we want to find the volume for that cone. Okay. And like usually for these problems, I will provide kind of like the initial picture. So like I would give something like this, like kind of labeled. But then you have to introduce extra labels for like to find the formula. But at least like kind of like a provisional preliminary picture I will give. Now, in this case, like this is kind of like part of the strategy. So if I have the cone in this way, like actually like let me see if like I can make this clear. So like if like what I was saying is that like the way we want to find the volumes is by making cross sections, right? So just like imagine, oops, sorry. Like actually let me just copy paste this code. Just to show you like kind of like that you do need to have like a good strategy for these things. So imagine that like the x-axis is passing through the cone in this way, right? And you kind of like want to cut the cone with like planes, like or like a piece of paper. So like just imagine you have a knife and you make a cut on the cone. Okay, so that is, if you kind of like set up the cone in that way, that is how the cross section would look like, but it is not super clear what that is, like if you think about, I mean, it does require some thinking about what this like shape is. Um, it's not so obvious, like, and even not even to me, like, I would have to think about it for a while. Um, so that would like, let me just say like that the cross section is a bit like hard to like like, it's like a hard to identify. Hard to identify. Well, at least for me. But if you rotate the cone, your life becomes easier. So for example, uh, if you set up the cone so that now like the x-axis passes through like kind of like the vertex, like this, like the what before what's the top of the cone, right? Then now if you do like a cross section, that is easier to like, identify as a disk if it makes any sense. Like it's just kind of like a smaller disk compared to the previous one. So like what I'm trying to say is that it does matter like kind of how you decide to set up the cone because you're trying to cut it, right? So like, not every cut is as easy to identify as others. Like, um, like you can cut the cone this way and like actually that's maybe that actually would be hard to find as well. Like, like you can cut like the cone like crazy. You want to cut it like in a reasonable way. Like usually there's not that much like, either like it's like either you keep it vertical like in the original position or just try to rotate it. Like either one of those two will work. It's not that anything like insane will happen, but you know, now the cross sections are disks and that is easier to work with. Okay. That making sense. That's just about so far so good. Okay, and then the again, if you think of this disk being like at a distance x from the origin, like it does make sense for this problem to like align to put like the origin like at the vertex of the cone. So that like the integral goes from what? From like 0, like again, before this was the height, so when you turn it upside down, this like interval is like h. So here, like I have h. So that's good. Whatever we do, we have to do a definite integral from 0 to h. That's kind of what this is telling us. So the goal is to find a formula for the area of this disk in terms of x. That's kind of like what we're trying to do. So that's the goal. Let me call it a of x. So like you want to find in terms of x. Is that okay? Is that making sense? And so like, it's not like super obvious at the moment because like x, like x is kind of like the distance to the origin. You know the formula for the area of a disk in terms of the radius of the disk. So it does make sense, even if it's kind of like adding extra variables, it does make sense to like include like a new variable which refers to the area of this disk just because it makes your life easier at the beginning. So it's kind of like changing the problem into something more manageable. So let me copy paste a picture. So what I'm trying to say is that if you say that this disk has radius r, right? If this disk has radius r, then we do know that the area of that disk is pi r squared, right? Okay. And so like what we're actually trying to do is like essentially finding a way to write r in terms of x. That's actually what we're trying to achieve. The moment we have r in terms of x, then we're good to go. And that is actually the difficulty of the problem. So it isn't like the difficulty is not in the calculus, it is in the, the high school geometry things, like because it's kind of like working with the diagram, which can be harder actually sometimes, like than just like doing like the integral, which is more mechanical. Is that okay? Is that making sense? Okay, so now this is where you do have to get creative. So what you can try to, and that's kind of like the way that I find it the easiest one in this case. Is that there's secretly two right triangles hidden in this picture. Like, so let me see if I can identify them for you. So the first right triangle, I'll color it. The first right triangle is this one. Okay. And the second right triangle is going to be this one. Like, actually, let me see if I can erase R for a second, because this is too much like stuff and it doesn't depend on R. Okay, like now it looks better. Is that making sense? And okay, so we can identify the size of those triangles, right? Because the first right triangle is X, R, right? And then the hypotenuse, whatever that is. Like, I don't care what that is actually, for now. And then the second right triangle, what are the sides for this one? Okay, so you need to know the length of this side, right? This side is just the height of the cone. So the first one is H. Okay, so this one is H. Then you need this side, right? That is actually the radius of the cone, like the radius of the big cone. If you remember like this came from the base of the cone, which has radius R, like R, but like R in the sense of like capital R, like, like uppercase R, not lowercase r. So this one, let's put it here. So you do have those two angles. Sorry, those two right triangles. Is that making sense? Okay, and how are they related? Okay, well, there's this thing that the triangles are similar, but who will remember that? No one. What you can do is like, if you call this angle theta, it is the same angle theta on both. Like, and then you just use tangent, because tangent relates these two sides, and then you're done. That's actually what trig functions are for, to talk about similarity of triangles in a more convenient way. So if you call this theta, it is the same theta. Like, it's kind of more clear, like, like, I mean, it is the same angle for both of them. So the tangent can be computed in two different ways. And that's kind of like the key. So what is tangent? In general, the tangent is like the opposite side, right? Divided by the adjacent side. So like in the first triangle, that's R divided by X. But if you had used the second right triangle, that would have been like big R divided by H. And this is kind of like the most important part of the problem, actually, because it relates all the variables that you have in the diagram. Is that okay? Is that making sense? Questions up to this point? And so why is that useful? Because from this equation, you can, like, if you just focus on this equality, you can solve for little r, which is what we needed because that was like the area of the disk. Okay, so that says that little r is like multiplied by x both sides, so you get r over h times x. Okay, and so the area of the disk, which was pi r squared, becomes pi times r over h times x squared, right? Which is, I mean, if you kind of like work this out a little bit, is pi r squared divided by h squared times x squared. Okay. So this is like the area. Let's call it area. And so now this gives you the area in terms of x, which is what you wanted like originally. So like, again, like I think I can do the picture here if you want. Ah, I still had the picture. So what I'm saying is that the area, what we just found is that this disk, right? This one has, like, this is like the area of that disk. But like the cool thing is like it is like in terms of like x, not the radius of the disk. Okay. Does that make sense? It does make it like, you know, if you, especially at the beginning, if you're not very confident on what you found, it does make sense to kind of like test it out in special cases to make sure whether it gives you something plausible. So, you know, what if you put x equals 0? If you put it, remember, x is like the distance to the origin. If you put x equals 0, like you're moving this disk, right, towards the origin, and the disk shrinks, right? So it becomes like a point. So at x equals 0, the area is 0, right? And that makes sense because it's like literally like the vertex. What if you start moving the disk towards like the base of the cone, right? So you move the disk here, you move the disk here, you move the disk here. So if you put x equals h, right? If you put x equals h, the h's cancel, and then you get pi r squared, which was like the area of that disk. So it's kind of like useful, like for these problems, to test the kind of like the extreme cases to see whether you have like a formula that works. So, but once you get to this point, like it is like a regular integral that you just have to do. So like the volume is, again, like in this case, it would be like the integral from 0 to h of the area with respect to x. So this is like the integral from 0 to h of what is the area? Is pi r squared over h squared times x squared dx. Okay. All of, like, again, like you have to imagine that like the radius is known, the height is known. So all of this is like a big constant, which you can take out of like the integral. So and as I was saying, like actually the integral itself is not too bad. It's like usually like a standard integral. Yeah.
So when we calculate is R. So
Uh-huh.
could we also just like write the equation for the straight line?
Right. Actually, yes, one of the workshop problems on Thursday is kind of more like that. So yeah, like another like alternative, which is also useful. Yeah, it's like that's a good like observation. Like if you call this point 0, 0, this is like the point what h comma r, and this would have been like the point x comma r. Right, and then if you find the equation of the straight line that goes through these 2 points, like that's also like a right. That's a good trick. Yes, also, which is like where did it come from? From the tangent, because like the slope is the tangent of the angle, right? So it's all kind of like the same, but Yes, like actually one of the problems on the workshop is more like I thought about it more in that way, but yeah, it's a good thing that you mentioned it because that is like another alternative, which also shows you there are different ways to set this up. It's not like a unique way. You just have to find the one that makes more sense in your head, like so sometimes it's better with that. Like, if you remember angle similarity, you don't need to do anything. Like, but who remembers that? Like, so I'm not counting, like I think tangent is something more familiar, so that's why I'm using tangent. But yeah, there are different ways to kind of like get to the correct relation between the variables. No, but that's good. And then this is like not too bad to integrate. So like the integral of x squared is x cubed over 3. I mean, well, of course, there's like a constant of integration, but I'm totally forgetting these constants of integration because I just care about like definite integrals for most of at least at this point of the course. So when there are definite integrals, like the constants like of integration that you add in the antiderivative, like they go away. So like it doesn't matter. And so you get pi r squared h squared times h cubed. And then it gives you, oh, sorry, the 3. And then, so that gives you 1/3 pi r squared h. So this is the volume. So it's like a useful formula. So let me put it like, put the diagram again. So what we just found is that if this has like a base of radius r and height h, the volume is 1, which is a formula you may have seen before, by the way. The volume is 1/3 pi r squared h. So what that means, well, sorry, before I say what that means. Is that making sense, kind of questions about this? Okay, so first, that actually, again, shows you the advantage of like working with like labels for everything instead of numbers. If I had said like radius is 2, h is 1, like then you just get what? 2 squared, which is 4, 4 times 1, right? You get 4/3 pi. And so what? Like that doesn't kind of tell you how the number depends on the radius and the height. It is more clear from this perspective because like it kind of like this will work for every radius and every height. So it's kind of like more elegant to have gone through like the extra work to find it, like regardless of like which values you had. And also the dimensional analysis is more direct from here because this has dimensions of length squared, this has dimensions of length, so length squared times length is length cubed, which is volume. So it also like if you have like if you have like the actual formula for like the variables, it is easier to check that you got like the right answer and not like I made a mistake. So this still has like the correct formulas, like sorry, the correct units. So this is like still length squared, and then this is like length. And length squared times length gives you length cubed, which is what you would expect for volume. So like that's also like a better like working in this format actually helps you out because it kind of prevents more mistakes from happening. It gives you more tools to check whether you get something that's plausible or not. The other thing I wanted to say, which is kind of like a nice like just like a cute fact, is like what that formula says is that if you compare the cone versus like the corresponding cylinder with the same radius and height, right? What is the volume of a cylinder like that? It's just like the area of the base times the height. So like what this formula says is that the volume of the cone is 1/3 of the volume of the cylinder. And this is volume of the cone. So like the volume of cone is 1/3 the volume of the cylinder. So what that means is like, if you actually build these things like these solids with some material like copper or gold or iron, whatever, and you melt it, the cone, then 3 of these cones like would fit in the cylinder, like you could pour the melted, like, gold and like pour it into the cylinder, and it has like 3 times the amount of volume. So you could put 3 clones of the cone in there. But those are kind of like the kind of relations that they're nice to find this way. But yeah, like in the workshop, I'll give you like others like of this sort for you to think about, but like, a lot depends on just like how you set it up. So that's where it is more like, can be more confusing because you do have to make some choices, how to start the problem. And that can be generally difficult, like, like it's not like, it is harder than just like integrate X squared, like that's like the easy part of the problem. So like the calculus part is actually not too bad. What is a bit harder is like the geometry part, like the setup of the problem. Is that okay? Are there any questions about this? Okay. So there is like another way to find, I mean, there are tons of ways to find volume, but at least in this course, there's like another way for finding volume that we will discuss, which is called like the cylindrical shell method. So I'm we'll start it out today. At least try to get to the formula because that is a bit trickier to explain. So it requires more animations. So here's like another method for finding volumes. Which is called like, again, the cylindrical shell method. So okay, so let me oh, sorry, yeah. Right. Most likely, yeah, I would give it like, correct. Right, like it's more like I'm more interested in like you giving me like the formula in terms of the radius or the height or whatever, like relevant. Yeah, exactly. Yeah. Because like the actual numbers per se, like really like 85% of the difficulty is like in the equation that relates the variables. And it kind of like becomes messier if you put like 4 or 3 or like, like actual numbers, like kind of like hide more of like what's going on. So I do find it more helpful to like, yeah, but I do like if I give like a problem of this sort, I will give it in like, called R, the radius, and H, the height, or like whatever. But yeah, like so will be more in that sense. So that you can kind of like appreciate what the formula ends up being. And it will also say, oh, I want you to find the volume using this cross-section method, or I want you to find the volume using the shell method. So which is what I'm about to explain. Would you like that or something?
Under R squared, you have length squared, under H, you have length squared.
Oh, right. Oh, the advantage of like having these with the actual variables instead of numbers is that you can keep track of the units. So the idea is like the radius has units of length. So when you square it, you get length squared, and the height has units of length. So that kind of guarantees that whatever this formula is has like the right units. Because it would be odd. Imagine if you made a mistake in the integration and you put R times H. That has units of area. And then immediately tells you it was a wrong formula. That is something that gets lost if you just have numbers. If you just have numbers, like you cannot keep track of the units unless you literally are writing 2 meters or 2 feet. Like, but who wants to do that? Like, it's nicer just to do this like once, like, So like the formula E, that is like the nice thing about like keeping like, in fact, like before I give you the cylindrical shell method, like that's kind of like integrals are supposed to work in general. So like maybe I'll put it like as a tiny remark. The idea is like the units, like whenever you have like an integral, the units of like an integral, is like the units of the function f times the units of x. Which most of the time we are thinking of x as being like a length. But like sometimes you can do like an integral with respect to time. That's what I think you did that in Calc 1 when you find you're giving the velocity and you want to find the position in terms of time. So like, kind of like the way how integrals work is like the units multiply, whereas for derivatives, the units divide, right? So like when you have like a derivative, let me see if I can move this like a little bit like down. Oops. like again. Whereas if you have like a derivative, what are the units of like df dx? They are like the units of the numerator, so like the units of f. Well, not numerator because it's not really like a ratio, but you know. So like units for integrals multiply and units for derivatives are ratios. Which is why this notation is like a useful notation for the derivative because like it reminds you of this formula for like that units. So that's why, for example, when it is the x dt, which is velocity, it's units of length divided by units of time and things like that. So like it's kind of like a good way to keep track of those things. Okay, so far so good. Questions about this? Okay, and let me just check the time. Okay, so I still have like 30 minutes. So at least I think I can get, I will explain the setup of how to find the volume in this approach because it is a bit more confusing than the previous one. So let me start slow because like, yeah, it takes more time to like know what's going on. So and it's harder to make the picture, so I'll kind of show you some animations on the computer. So like the picture I'm about to do is like not the most like interesting one, but it's like good enough for me to draw it because otherwise it's like a bit complicated. So let's say that you have like the graph of a function of one variable. So let's say you have y equals f of x. Okay. And here you have a and b. And then, you know, you have let's see, where do I have this? And then, okay, there's this region, right? Like, which is kind of like the one that you would work with when you were trying to find like integrals, like, right? Like the area between the curve, or like the graph of the function and the x-axis or like the interval AB, okay? So like imagine that you have the region, we can call that R, like, well, R and something like region. And so like the idea is that you want to think that you rotate this region about the y-axis. So like, again, I'll show you on like the computer how that looks like because it's hard to me to draw a picture, although I'll try to put like a picture on the notes. But just imagine like, you know, you could lead like kind of like, you know, the x-axis is not like fixed, so you can start rotating like the entire thing with respect to the x-axis. So you just take this and start rotating it, which I'll show you how that looks. I don't want to ruin the animation, so let me just put this display for a second on hold. Because it's kind of like nice to see what happens here. Okay, yeah. Okay, so let me, like, now it's ready. So let me go back to Zoom. Okay. Okay, let's see what's happening. So like, for example, think of, like you have like the graph of a function, like maybe that's how you know, that is how the graph looks like. And then you have this interval, which may, well, in this case, since the x-axis is here, this could be from 0 to 2 or 0 to 1 or whatever. So you have this region on the xy plane, and you are going to try to rotate it with respect to the y-axis. So here, like, it's going to show you, this side is going to show you the rotation, like as it takes place. I think it's that one. So like, this is going to control like how much you have rotated like the region. So let's see this happening. So you have rotated here about like 90 degrees, right? And then you keep going, 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 you keep going. Now we're like at 270 because let's say, oh yeah, it does allow me to go like, I like it when it does. And then you keep going, 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 360, then you're back to where you started, right? So that is what you call like a solid of revolution, something that you literally revolve about one axis, usually the y-axis for this case. So the idea would be, okay, given this region, right, how would I find the volume of this solid of revolution? As I said, it's just like it's a bit hard to draw this, like, on the iPad. So it's why it's better like to look at it on the computer. Is that making sense? Kind of so far so good. So I'll kind of continue with this animation before writing anything on the iPad. So like I don't have to be switching back and forth between like the computer like and the iPad. But the idea again is that it's kind of like don't freak out. You just start with the calculus, right? So like the idea of calculus is always to break things into pieces. So let me just return to the starting point. Okay, so this was the original situation, right? Like you have like the solid here. So again, to find volumes or areas, you break the region into pieces. So I'm going to break the original region that's about to be rotated into rectangles because that's, like the integral was related to rectangles, like for like on the plane. So let me see if I can. Yeah, but I don't want. Which one do I want? This is not. Let's see. There are too many of these. Okay, that looks better. So like, you break this region into rectangles, right? And then like you imagine, okay, because rectangles are easier to understand, that's the thing. So just imagine what happens as you start rotating the rectangles. So just keep attention to. Oh, okay, this kind of doesn't show, it does, does it show better? Okay. Well, so let's see. I think oh, okay. That's one of the. Yeah. It's like I'm trying to be like, okay, which one do you? Yeah. So thank God, because it's like animation is so confusing to use. Like I'm trying to remember how to do it. So like imagine I just fix your attention on one of these rectangles, and that's like the one I'm about to rotate. In fact, like just to make it more clear. So I don't know if you see what's going on. Like kind of like you're getting some like it is related to like a cylinder of sorts, but it's kind of like what is called like a cylindrical shell because it's not all the inside of the cylinder that's being included. It's just kind of like you had like a cylinder and you cut like apart from inside of it. So it's kind of more like a hollowed out cylinder, you see? But oh, perfect. So what I was trying, it's more like a ring, right? It's like which is called like a cylindrical shell. So and the idea is to think of the volume as being approximated by, like the volumes of these shells, like or cylinders, which again, I don't think this like allows me to do it, but like, kind of like it, like I wish they kind of show you like how it happens when you have like multiple at once. But it's kind of like a nice animation. I like it because it kind of like shows you what the strategy is. So like the strategy is just to summarize what's going on, and I'm about to write it on the iPad. But break the region into rectangles. Once you break it into rectangles, one of these rectangles, when it gets revolved or rotated about the y-axis, it gives you like a shell. You find the volume of one of these shells and then you add them together because that's how calculus works. And that will approximate the volume. So at least let me write down like the formula today, and then next time I'll do the examples, because I don't think I have enough time to do the example today, but I do. This is one of those things where like you kind of say like the formula once, where it comes from, and then you can forget about it. So it's not that that's why like it's not something to worry too much if like not every step made sense. But you can watch the recording also. Because it does like it is like a little bit like trickier to like understand. Let me see. Try to do this again. Okay. Perfect. So the idea, so again, what I was saying, I'll kind of show like the picture a bit like bit better. Again, I'll do it for something easier, just for me to kind of like draw it, have like a better chance of drawing something that's relatively realistic. So, but it doesn't have to be like a straight line, like the graph, as you could tell from that animation. So like what I'm trying to say is that I'm going to rotate this. This region. And once you rotate the region, let me see where I have my picture to try to follow it, because it's a bit tricky to do. Here you are. So once you rotate the region, as you can see, it's not like an ideal picture of what's going on, but it's like a bit hard to draw. So kind of, you can see what I have in mind, hopefully. Okay, so that is like the volume that we're trying to find. At least I'll try to put this here. Okay. Want to find this volume. Okay, so what is a strategy? And again, I'll just do the rectangle thing one more time. So the idea is like once you break the region into rectangles, break region into rectangles. And let me focus my attention in one of here. Okay. So when you rotate the rectangle, you get like the cylindrical shell. Again, watch the video because it's confusing to see this here. But let me see if I can draw the shell. This is like a bit easier to draw actually, so. This is so hard, honestly. Okay, kind of hopefully makes some sense of what the picture is like. But again, it is like a bit hard to kind of like visualize. And so what is the volume of this shell? So how should you think about this thing? Like what happened is like you took this strip, think of this as like a vertical strip, which you rotate, right? Uh, so if you think of like the strip being like at a distance x, you know, like suppose like the strip, it is like at a distance x from like the origin, and it has some thickness dx. Okay. So what is the first let's just like understand the area. Like what is the area of this strip? Again, like the area of the strip is height times width. The height is the function, right? Because you're looking at the graph of the function. So this is y equals f of x. Times the width. So that is like the area of the strip. Okay. And so once you rotate it, you get kind of like you get like this circle of radius. Like what is like the radius of the circle is like is x, because like that's kind of like the like how big this segment is. So like you get kind of like this inner circle of radius x, and that is kind of like you're sweeping out this strip along, like using that circle like as you rotate it. So essentially, this circle has like a circumference. Like let me see if I can put it here. You have this circle of length 2 pi r, but like the r is x because like you are at a distance x from the origin. So like the volume of this, like of this shell is like the area of this strip times the length that you kind of like sweep it out, and you sweep it out an amount equal to the length of the circle. So it is kind of like the circumference of the circle times like the area. So it's kind of like 2 pi x times like the area of the strip. Is that making sense? Kind of like it's a bit harder to like, like understand. Oh, actually I have iPads here. So I have like, thank God I have this here. So this is like the y-axis. So I'm just saying like, you're trying to start rotating the iPad, right? By how much distance of the iPad travel? It travels a distance equal to this length. That's like kind of like the amount of the sweep out. So the sweep out is the circumference of the circle, which is 2 pi x or 2 pi r, because like here the radius is x, times the area of the strip. So that's like, again, like if this formula doesn't make a lot of sense, like 100% sense, like it's something like takes some time to digest. But I do want to write it before like wrapping today's class. So like the area of the strip was f of x dx, and so what is the volume? You integrate, right? Because like so like the volume is like the integral from a to b of 2 pi x f of x dx. Okay, where again here like you thought about a, and this is where b was. Sorry, maybe I should, yes. But like I don't want to put those numbers here. There. So but like the way to think about this formula is kind of like this is kind of like area, and this is like the length of the circle base kind of thing. So again, like that have like area times length is volume. So at least it does have like the right units. So let me check this is fine. Yeah, that's fine. But okay, so which again is like the formula itself is not necessarily that much more complicated than the previous one with the cross sections, but it does take more of like mental gymnastics to understand where it comes from. So like you do have like I'll send you like the link to the animation if you want to play with it. Yeah, sorry.
So that volume is that's the volume that you get when you rotate the whole function. Y-axis.
Correct. Well, not the whole function, at least a part of the function between x equals a and x equals b, right? Yeah. So sorry, just to make that, and I'll finish with this. Right. if you, you just focus on this part of the function between A and B. Right? And as you start rotating it, that gives you like the solid that you saw in the animation, and that has volume equal to this. Once you rotate it with respect to the y-axis. But of course, if you give different bounds, then the volume will change, but yeah. But the idea to think about it is kind of like, if you broke this into strips, like rectangular strips, and this is kind of like, the volume of one of these rectangular strips. That's like the better way to think about it, and then you're adding it together.
Would DX be the width of the rectangle?
Yeah, sorry, it's like there, but I can put it like here in this picture. So yes, the x, you're thinking of the x as like the width of like one of the rectangles when you do like the cutting piece. So, right, so it's kind of like understanding like, when you, basically it all boils down to that, when you have a rectangle and you rotate it about the y-axis, what's the volume? The volume is this basically, but that's what it takes a little bit of thinking like to see. Okay, so again, I'll do like an example, like 1 or 2 examples about this formula next time. So let's finish here. So I'll start from like this formula on one day. And yeah, we'll do that at the beginning of class and then do a few more things. So I'll send you like the notes later in the evening and also like the recording. I think this time the recording should have worked better because I figured out like anyone tried to see the video last time the iPad, but I think it should be fine this time around. So yeah. Yeah. It's on cam, like you have to read the announcement. Well, okay. Do you have a Canvas there?
Yeah.
Oh, no, it's not on the file, it's on the announcement itself. Yeah, but you have to open the announcement from the computer or iPad because if you open it from the phone, you won't see the YouTube. Let me just, no, you're good.